one more comment I want to make on the linearly separability question, since it was a great question. Actually, I don't want to make that comment. Yes, I've told you one way. There's definitely other ways to deal with linearly separable data. Another comment on the perceptron is it doesn't converge to the SVM solution, nor does it converge to, if I add in this thing, to the soft margin SVM solution. Can I change algorithms, have online algorithms that converge to the SVM soft margin solution or hard margin solution if it's appropriate? Yes, I can change algorithms. But interestingly, they have the property that they converge to the right thing, but then their predicted performance isn't quite as good. This is why I predicted the perceptron is better in this online setting. Okay. So what I'm not going to do, especially since I'm running short on time, is so we have this previous bound. I think it's easier to work with in this form. We can use this bound to prove a bound on the perceptron's performance on learning disjunction. Let me sketch how you would do that. R squared corresponds to the maximum norm of the x instances squared. So I have minus 1 or 1 n times, sum that up. That's equal to n. I take the square root, that's the norm, but then I square it. That's the norm squared. So r squared will be n for us. Okay. Then if we're learning k-literal disjunctions, we know that the k-literal disjunction is basically u with 1, 1 in your relative thing. So that's order k here. But somehow you're going to also have to include a term for the threshold. So you need to include that threshold term by using a threshold map. But u squared will be order k, but you have to include a bias term at the threshold. And doing all that arithmetic there, I'm not going to do for you now. But I encourage you to try to prove this bound of order k at for monotone disjunctions with the perceptron. It follows the arguments that we made in class. We'll get some more details. So we might introduce the bias term. In fact, you can show that there's a lower bound, that there exist data sets such that are for instance, compatible with a single disjunction, but that the number of mistakes that the perceptron will make is order n, even though a single disjunction fits your data. Likewise, if you use an online SVM, you'd have the same issue. You imagine you see a new data point, you update your SVM, there's still example sequences such that even though there might be a single disjunction x1, for instance, compatible with your data, your algorithm still will make mistakes linear in the dimension, which is kind of bad, because you imagine you have some very high dimensional data, and if you're in the worst case, you're going to pay in your bound linearly in the dimension. And we know with disjunctions that's not possible. I mean, it's possible to avoid that, because if we have a very computationally expensive algorithm, we can pay log n choose k, which is ordered k log n, so we don't pay linearly in the dimension, but logarithmically in the dimension. Now we're going to show an efficient algorithm rather than an inefficient algorithm, which is inspired to work where we pay logarithmically in the dimension. Okay? It looks, now, the way I'm doing this analysis, because it's going to make my life easier, is I'm only doing it for disjunctions. Whereas for the perceptron, we did generally for linearly threshold functions. Now I'm restricting the case to disjunctions because it's easier to do the analysis. But there is an analogous proof for linear threshold functions with Winnow. Okay. So let's look at what this algorithm is. It looks quite similar to what we've done before. our W's will all start out with 1. Now, because our analysis works easier in this direction, we're going to, instead of using -1 and 1 to represent the disjunction, we'll use 0 and 1 to represent a disjunction. And we're going to we're going to introduce a threshold. So we're going to predict if we're going to, if we get some instance in 0, 1, and it's more than 1, we're going to say predict true. If it's more than n, we're going to predict true. Otherwise, we're going to predict false. I.e., so if we have a lot of 1s and our W vector has a number of 1s or large values in it, we're going to tend to predict that this is true for that disjunction. Okay? And then, just like the perceptron, if we make a mistake, what we're going to do is the following. If we should have predicted, if a given xt said 0, but we should have predicted true, we're going to double its weight. In the other direction, if we make a mistake, and the correct label was that this wasn't a true instance of the disjunction, we had 0, yt will be 0. If we predicted, did I do this backwards? So I have a negative. Basically, in the other direction, we have to half the weight. Okay, so if we compare this to the perceptron, when we get an xt value, we essentially either it's kind of like we add on the xt value times the yt value to our predictor. Now in this case, it's a little bit like, I can make this formal, but I'm going a little bit quickly. It's like multiplying. It's like a multiplicative update instead of an additive update. Okay? And we're going to show with this update that we'll no longer have this linear dependence on dimension. Okay. So the bound works by in the same way, roughly, that we did things before. We're going to bound, but we'll do it slightly differently. We're going to bound positive examples, and we're going to bound negative examples. Okay. So suppose it was a positive example, and we made a mistake. Okay, i.e., it was a positive example, and our disjunction was x1, x2, or x3. That means that we didn't predict some value that we needed to get something more than n, and one of these had to be 1. Whenever we make a mistake, one of our relevant attributes must be doubled on that mistake. Why is that? Well, it wouldn't be a mistake if none of our relevant attributes didn't have a 1 value in them already. Okay, so at least one relevant one is doubled. Another observation on a positive example, where relevant are those corresponding to a disjunction that fits the data. Just like the perceptron doesn't know V or G. The window doesn't know the relevant variables, but we do the analysis in terms of what we know the relevant variables are in retrospect. Relevant weights also never decrease, because they can only decrease on a negative example, and I'm going to go quickly. Likewise, once we have a relevant weight above n, it will never change. Why won't it ever change? Once its value is above n, if we ever had a positive example and that was given as an and we saw a 1 there, we would have predicted it correctly because our threshold value would be more than n. Okay? So our relevant weights never decrease. They double whenever a mistake is made, and once it's more than n, they'll never change. So how many times can they do that? Well, if there's k relevant variables, or if our weights start at 1, they can only double log n times plus the plus 1 for rounding issues. So we'll make mistakes on positive examples no more than k times log n times. On negative examples, the argument is more subtle. Now we'll take the sum of the weights. So WTI will be the sum of all our individual weight variables. We'll let MF denote the number of mistakes on negative variables. W1, since all our weights start at 1, is n. Okay. On a positive mistake, on a positive mistake, our new value of the weights increase by no more than n. Why is that? Because we predict Wt.xt. We predicted that it was, we had a positive mistake if Wt.xt was less than or equal to n. On our updates there, we double weights. So if we double the weights, we can no more than double Wt.xt, and that value is already less than n, so that the relative weights can increase by no more than n. We have a similar argument on negative weights. On negative weights, on a negative mistake, we should have predicted a value less than n, but we predicted a value more than n. Once more, we're having weights. We're having weights whose sum total was already more than n. So if we're having weights whose sum total was more than n, we must have at least n over 2 weight. Okay? So we have these two terms interacting. The number of times we have a positive increment is the number of mistakes on the positive side. So we get MP times n is an upper bound. The number of times we lose at least n over 2 is MF times. This gives us a weight on the final weight. The way the algorithm is set up, we're always multiplying or halving. This is lower bounded by 0. Rearranging these, rearranging, we can, doing a little bit of algebra, we can go ahead and prove that from this equation with the lower bound of 0. So then we have a bound on the positive. This is quite fast. Standard proof, which you can find many places, but you need to read and think it through. If I talk it fast, it's a little bit magical. MP plus MF, we're just summing these two terms. So we've upper bounded the positive weights and the negative weights. And the feature that we have now for these positive disjunctions is we now have a term that's logarithmic in n. Okay. Okay. A little bit of background. Learning disjunctions. let's think a little bit about this page isn't in your notes. I'm sorry. I thought this would be something great to tell you. I realized this last minute. Even though we're giving these bounds in terms of predicting as well as the best k-literal disjunction, we might ask ourselves, well, how easy is it to find a k-literal disjunction that's consistent with our data set? This is the feature selection problem. Having a disjunction, you know, how easy is it if you have a 1,000 variable data set and you want to find the minimum features that are relevant to your data set? It turns out, at least in a computer science perspective, this is hard. We'll sketch why this is hard. So the reason why it's hard is there's some reduction from finding consistent. Yeah, our algorithms predict as well as the best k-literal disjunction, but they don't find one. They don't find that minimal disjunction. How do we argue this? We argue this from set cover. We'll do this with a picture in a moment. But so we have some set of m elements, and we have subsets of those m elements. And the question is, what's the fewest number of sets that we can choose so that we cover our original elements? And I'm going to claim that this then corresponds to disjunction finding. But let's look at a picture of set cover first. Okay. So this is a picture of set cover, which I stole from somebody's algorithms class. So imagine you're hiring some people for a job. Person 1, person 2, person 3, person 4, person 5, person 6. Each of these people have different skills, okay? And the point is, you need all 12 of these skills for your business to run well, okay? You know, person 1's graded at tasks 1 through 6. Person 2 is graded tasks x5, x6, x8, and 9. What's the fewest number of people that you can choose so that you manage to cover all the things that you need to be done? Finding that fewest number of people, I'm not going to prove for you as an example of an NP-complete problem, the decision thereof. That means, for those of you who don't do computer science, is roughly you need an exponential algorithm to do this in the worst case. Solving set cover, if you could find disjunctions, you could solve set cover. Therefore, finding consistent disjunctions is a hard problem. We'll see this pictorially in a moment. But basically, the problem of finding a k-set cover reduces to the problem of finding a k-literal disjunction consistent with a set of examples. Not exactly the way you first think, but I'll illustrate with a picture. But basically, we have our standard data matrix, so we have m instances of n dimensions. Then the n columns are the sets, and a consistent disjunction is a set cover. Let's look at this pictorially. So, I mean, that's all there is to the reduction. So this previous example of a set cover problem, let's represent as a data matrix, okay? So observe that x1 is a skill that person 1 has and person 3 has only. Going to the picture on the next slide, so I've represented x1 as being a skill that person 1 has and person 3 has, but not P2, P4, P5, or P6. Okay. Likewise, here, x11, person 4 has this skill, person 6 has this skill. Hopefully, going back here, I have person 4 has this skill, person 6 has this skill. Okay. So I'm representing the sets as these Boolean vectors, okay? Now let's go back to the previous slide. Let's talk about what a set cover is. A set cover is we have to cover all the elements. So for instance, orange covers with the blue covers plus the pink covers and then plus 6. So I can't do it column-wise. Otherwise, I could choose what's another cover? I don't know what another cover is. But the point is, you choose, you have to cover each of these in sets. Okay. So going back to this table now, P3, P4, P5, for instance, in the previous set, is a set cover. That also corresponds to a consistent disjunction, where this is a set of only positive examples. How can we see that P3, P4, P5 cover? Because look, X1 skill is covered by P3, X2 skill is covered by P2, X3 skill is covered by P5. Go all the way down, we see that each of these skills are covered by one of the people in there, okay? So, if I had a way of finding this disjunction, I would have a way of finding a set cover problem when put in this form. So, finding a minimum consistent disjunction is a hard problem computationally. We can't expect that that's what the perceptron or a support vector machine will pop out, or if we use lasso or we use something else in the generic case. But what's interesting is the guarantee on the mistakes that either we make with the window or the perceptron are in terms of this variable k, which is exactly the size of that minimum consistent cover. Okay. Questions? Okay. Okay. DNF, big open problem in machine learning. How can we learn more complicated Boolean concepts? Let's learn DNF. Okay. With a sufficiently large DNF, we can learn anything. With a small DNF, well, it seems like a reasonably expressive concept. Let's see how we can use what we have done so far to learn DNF. Okay. We can learn DNF with the kernel method. Okay. Here's our binary features. Okay. Recall DNF is a disjunction of conjunctions. Our feature map that we're going to use, phi of x, will map x into the set of all possible conjunctions. Each term in our feature map corresponds to some positive conjunction. So our feature map is 2 to the n dimensional. Okay. Our kernel function needs to compute the inner product between on this 2 to the n dimensional feature map. You're lucky when the kernel exists for the problem that you want. It turns out that this very simple looking function actually operates over this 2n dimensional space. Let me explain how that's possible. Okay, let's recall DNF. Example DNF. DNF is a disjunction of conjunctions. So what we're learning is something like I'll use U this time. U1 conjunct with U3, U5, or U2 conjuncted with U7, U8, or and so forth. Okay. So we're learning a disjunction of conjunctions. So our feature map on x1 dot 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 xn maps to this 2 to the n dimensional feature map, which is just the one vector for the empty disjunction. We have the disjunction x1, we have the disjunction x2, dot dot dot, we have the disjunction x1, the xn. Then we start to have larger order conjunctions, x1, x2, x2, x5, all of these, dot, dot, dot. We get to the third order ones, we get x1, x2, x3, and so forth. So we have this huge feature map. The claim is if we have two instances here, we can compute it with this A over kernel without literally implementing it as a 2n dimensional feature map. How does this reduction work? Why does the product from I equals 1 to n of 1 plus xi to the yi compute phi of x times phi of y? This is an order n computation here, very small. But the claim is it actually does what this feature map is. Why does this work? We have all possible terms in here. So what's some possible term? Some possible term, for instance, is x2, 4 being dotted with y2, 4. Times it, and then we're going to sum up all sorts of terms. This is what one sample term looks like. Where will that term come from in this feature map? Well, when we're on x, so what does this look like? This looks like a product. We have a product of 1 plus x1 times y1 times 1 plus x2, y2 times 1 plus x3, y3. Sorry, I want to get 4 in here. 1 plus x4, y4, dot, 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 1 plus xn, yn. Okay, so to get this, now what happens when we do this product? Well, we'll have some term that looks like 1 times 1 times 1 times 1 times 1. Then we'll have some term that looks like x1 times y1 times x2 times y2, blah, 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 all the last terms. Otherwise, on each individual term, we're either grabbing this or we're grabbing a 1. Grabbing this or grabbing the 1. So each term is going to correspond to us grabbing either this or that. So, for instance, to grab this, on this term we grab a 1. On this term we grab the x2, y2. On this term we grab a 1. On this term we grab the x4, y4. All the other terms we grab 1s. This is one of the terms of this product. Likewise, any other pair in there, you just grab the terms. And so this is the quick argument that another thing to think about, that the ANOVA kernel computes this feature map for us. And this feature map, we have all conjunctions, and we have an algorithm that learns. We have two algorithms that can learn a disjunction. okay? And our feature map is all conjunctions. So let's look at what happens. Perceptron algorithm, great. Our computation is fast because we can use this kernel trick, okay? And so the number of mistakes corresponds to k times the dimensionality of our data. But the dimensionality of our data is now 2 to the n, which unfortunately is huge. But on the other hand, the perceptron with the kernel, everything's order n, everything is very fast. If we wanted to do things with Winnow, great. We're going to get a good. So with Winnow, I don't know how to do this kernel thing anymore. I can literally expand everything out in the feature map, but I don't know how to kernelize those doublings and halvings in any way. That's the mystery. I can't do that, or I don't know how to do that. So what does that mean? So Perceptron had a mistake bound for k term d and f of k times 2 to the n. Pretty large. It's here. Winnow now is going to be k times log 2 to the n. Great. Log of 2 to the n is n. K times n. Not bad for learning k term d and f. I mean, it's great. But our running time is 2 to the n per prediction step. It's just the same thing as expanding things out. So summary, Perceptron, we got a great fast algorithm with a poor bound. Winnow, we have this slow algorithm with a very good bound. Okay, so we can sort of learning relative to the best expert, best disjunction, different loss functions. Perceptron and Winnow, this is a big dichotomy that happens elsewhere in machine learning. Similar algorithms, very different performance. We focused on tooling functional learning, but we can tell this story a little bit with disjunctions. And part 3 is not going to happen, nor will I discuss anything with graphs. Okay, if there's any questions, please ask them. Otherwise, I will see you after the interval where you will have a lab. And there's a